Well, good morning, everyone. This is EMX on the first Monday of December, last of the year 2024. And we have another great program, of course. Welcome, everyone, and people who are logging in from MRS in Boston at the same time. It's a favorable time difference, but not for one of our speakers who's coming in from China, where it's about midnight right now. Anyway, just to announce that our first EMX of the new year will not be on the first Monday as in previous years, but on the second Monday, January the 13th. And so we will see you all then. We'll send out announcements before and after the Christmas Hanukkah holidays. And I'd like to welcome everyone again and thank my co-organizers whom you see on the screen here, and pass the baton over to Wah, who will introduce our bio speaker. Thank you.
Okay, good morning. Happy Thanksgiving for those who live in America last week. This morning we are very delighted to have Professor Jose Rodriguez from UCLA to come to give us these lectures. Jose originally came from Mexico when he was in high school, and then he went to UCLA for undergraduate, graduate, and postdoc, and then stay on there. And he started as a biophysicist and then turned into a physicist, turned into a chemist, and turned back to the biophysics. And he has done some amazing piece of work using microelectron diffraction and other imaging technique to study biology. And he's a very well-known figure and one of the most exciting individuals. And he was listed and recognized by the Cell Press as one of the 100 inspiring Hispanic scientists in America. So and then he won numerous awards, including the Sloan Fellow and Packer Fellow, and so on. So it's our great honor today to have Jose to give us these lectures on the promise and challenges in microelectron diffraction for biological system. Jose, thank you for coming.
Thank you, Wah. Thank you, Bob, for the invitation. And I want to say that it's a real pleasure to be here to share with everyone some of my ideas and the work of my group, focusing on the promise and challenges of electron diffraction, primarily with an eye towards complex molecular structures, biomolecules, and even large complexes. And so I will say that my talk will span a great swath of chemical complexity, everything from simple small molecules to more complicated small molecules to molecular assemblies and molecular machines, but that fundamentally a lot of it is underlined by this idea that at the most fundamental scales, we can actually have those molecular assemblies have regular order. Sorry, I'm trying to get a pen here, but it seems like I'm annotating. You can have regular order and they can be crystalline, and this was identified early on. Of course, we've relied on crystallography for well over 100 or almost 100 years now. But as molecules have become more and more complex, we've faced challenges essentially based on the fact that the more complex molecules are not able to make large perfect crystals. And so the types of crystalline assemblies that we're used to dealing with have shrunk over the years. Of course, the response in the community has been to build bigger and better instruments that pack more and more photons into a smaller unit of space and time in order to achieve the greatest amount of diffraction possible from these small assemblies. And we benefit from many of those here in the US, including Stanford's own X-ray free electron laser at the LCLS. And so these machines have compensated for the fact that samples may be small by, again, packing as many photons as possible into a small unit of space and time, and to the extent that they essentially obliterate the samples the moment that they encounter them. And I'm not going to focus too much emphasis away from those techniques. They're fantastic complementary approaches, but I'm here to tell you about one alternative and that is the use of electron microscopes that are commonly available at many institutions across the world, and that while diffracting from your samples will not instantly obliterate them, although they will fundamentally impart damage. Electron diffraction is not a new idea. Going back to its first demonstrations in the 1920s, we've seen basically electron diffractometers be employed to interrogate small amounts of material. Arguably, one of the first experiments was done by George Thomson, who basically illuminated thin films of crystalline materials by cathode rays or electrons in a vacuum tube, and then put photographic film on the other end, trying to see deflections of electrons from the crystalline material. And I should say that the experiments that we conduct today are in some ways not too different from the experiment of Thomson in 1927. Of course, his premise was that he could determine unambiguously whether or not de Broglie was right, and determined that electrons are waves. And so we're thankful for those seminal experiments, and we've come a long way in some ways. For some reason, electron diffractometers morphed and evolved into something that looks more like a fridge in some instances, and in other instances, they've evolved into instruments that are not too different from Thomson's original prototype. And because of this evolution, we've also gained the ability to use electron microscopes to image single molecules. And I'm not going to belabor this point, but I think the resolution in cryo-EM has been tremendous for many areas of biology and chemistry, and rightfully was awarded prize, and was even sort of pointedly pointed out by this article in Callaway in 2015, that one of the great benefits of imaging molecules directly is that those molecules don't have to be bound by the limits of crystallography. So even when you don't have crystals, you can go around imaging anything you like. And this has been really transformative for many labs. Also beneficial has been the fact that there are dedicated centers for performing this kind of work. I'm listing here the 3 cryo-EM national centers, but of course they're complemented by cryo-ET national centers as part of a great network that is funded to facilitate the service of imaging molecules for the community or specimens for the community. And we have benefited from it as much as anyone else, especially for challenging samples that require the development of new methods, or samples that are not routine and ordinary, but are ambitious and challenging, and otherwise would be difficult to get time to image in other places. Now, diffraction at the same time has evolved, and while imaging is fantastic, it faces some fundamental challenges. In order to see the entire breadth of molecular structures, in other words, the chemistry of life, we have to be able to appreciate the fact that many of those molecules are too small even for the traditional imaging experiments. And so many of the types of molecules that we might be interested in are not easily resolvable by imaging. A great example is this peptide thiostrepton. It's a natural product, and many of my colleagues would say that it would be potentially impossible to image because its scattering is very weak and it would be lost in the imaging experiment. And so we benefit from the fact that with the very same instrument that you can image molecules, you can basically reconfigure the lens system to also collect diffraction patterns from ordered assemblies that are present in the microscope. And you can train your beam on a small subregion of a sample and collect a diffraction pattern. Of course, their crystals are doing the averaging and amplification of signal for you. And so there's some benefit to using crystals in a system like this. Ultimately, the goal is the same: to determine atomic structures of the underlying molecules that make up that crystal lattice. And so in practice, what you have is either a slurry of crystals or a powder of crystals that you could put on a TEM grid, and then you can screen that grid for things that morphologically resemble crystals or that may be opaque and resemble molecular assemblies, and then try to diffract from each of those, collect as many diffraction patterns as you can, typically tilting the sample to sample reciprocal space fully in order to collect enough data to determine a molecular structure. And this entire process can take anywhere from minutes to hours, primarily depending on the time required to identify and sample crystals on a TM grid, which at the scale of crystals of this size is actually quite vast and can take some time to survey. And so when conditions are favorable, you can end up illuminating a crystal like the one you see on this slide here. These are needle crystals of a peptide that is associated with the prion protein, and they've assembled here and been deposited on a grid. And you can illuminate one of these with the electron beam. You can at the same time tilt the stage and record diffraction patterns. And you can see this beautiful diffraction movie that actually has signal that extends out in resolution to about 0.8 angstroms. And again, in favorable cases, this type of data is sufficient to determine an atomic structure ab initio. And so this is the structure of that peptide here now self-assembled as a pair of beta sheets, that is features that are sort of prototypical of amyloids or prions, including a tight network of hydrogen bonds that we can see because we can appreciate where the light atoms are in this structure because of their relatively stronger scattering of electrons compared to X-rays. And so many people in the community have recognized this and have now applied 3D electron diffraction or micro-ED to materials, proteins, peptides, and small molecules of various kinds. And this approach is now thankfully implemented all over the world. I have a survey of some of the sites here and some of the types of experiments and molecules that are being interrogated by this approach. And I should say that this is growing daily, and so it's hard to keep track of where everything is, but it's really exciting to see growth in that space. Now, that sort of overview doesn't really touch on what I really want to cover today, which are the challenges and opportunities that we face now with this technology. And I'll break my talk into three parts. The first is new structures with potentially limited data or resolution. So can we determine new and interesting structures despite some of those limitations? The second part will be the benefits and challenges of using some of these new technologies that are now a mainstay of single particle and tomography. These are electron counting detectors or direct electron detectors. And the third is the determination of atomic structures from maybe imperfect, bent, or overlapping lattices, ultimately with the goal of trying to shrink the number of molecules required to determine an atomic structure. And so in this first stage, I'll say that a lot of our approaches are benefited by the determination of structures by new methods. These include the fragment-based molecular replacement approaches that have been pioneered by many, but in particular, Professor Isabel Ozón in Spain. And so we've applied these, obviously, in test cases like the one I'm showing here to determine the structure of proteinase K from fragments. This is from a data set that was collected from proteinase K that had varied in resolution from about 1.6 to 2 angstrom resolution. And so obviously we could get a molecular replacement solution of the whole thing because we know the structure, but from fragments we could as well. And so you can start with an initial model of about a dozen fragments and then stitch those together in a semi-automated fashion to get a final model of proteinase K that looks and very cleanly resembles the known structure. And so we know that this works in situations where you have known subsets of fragments from close homologs, but we've also demonstrated that it works even for chemical compounds that just have one small piece that is conserved. And so in this case, we see a specific natural product. This is nosaheptide, and we know that nosaheptide shares some particular features with other similar peptides like thistrepton. And so using some of those chemical motifs, we can use this principle of fragment-based phasing to get solutions for, in this case, nosaheptide that are fairly reasonable and match what we would expect the structure to be. And most recently, we've become particularly interested in mapping the types of structures that are involved or that involve biomolecules that are natural products and that may have the potential to act as inhibitors or blockers or deterrents of emerging pathogens. And so this work has been funded, thankfully, by the Howard Hughes Medical Institute as part of their Emerging Pathogens Initiative, and in collaboration with the labs of Yitang and Jose Nelson and others, we have been able to map out the interaction between some of these emerging protease inhibitors and their target proteins. In this case, we've used papain as a model cysteine protease targeted by this E64 molecule that essentially is able to, as an epoxy peptide, covalently bind to the active site cysteine of the papain molecule. You see diffraction here up to about 2 angstroms, and on the right-hand side, you see a difference map showing a clear difference for where the drug would bind. We've actually been able to show that you can rapidly screen and soak crystals or pre-existing crystals of these molecules that are in a slurry. You can soak them either preceding their deposition on a grid or directly on a grid. And within a few minutes, you have sufficient occupancy to be able to see in maps of the structure some signal for the peptide. And we found it especially advantageous to be able to use complementary methods like mass spectrometry to actually sample directly the crystals on the grid to be able to identify bound states for the molecules that are present on that grid. And so we've actually used that to even discriminate the binding of specific molecules, in this case, again, E64 to its target, over other potential molecules in a slurry, indicating that this is a very sensitive way of identifying the specific binding and interaction in the context of soaking with mixtures of compounds. And so we're really excited by this because we think that as a screening approach, it's actually rather facile and allows us to potentially identify novel biosynthetic ligands and natural products. Now, this next section speaks to the need to identify these signals as accurately as possible using new direct electron detectors that give us the best possible interpretation of our diffraction patterns and measurement of our diffraction patterns. We're not the first to think about using these detectors. Of course, these have been used extensively by single particle analysis and tomography now. The challenge with these detectors has been, and every time we tried to use one of these detectors for many years, we were told that there were two issues. One is that there was coincidence loss that would plague our use of these detectors. And the second was that we would probably burn a hole into the detector from the diffraction spots. And so to overcome these challenges, we and others in the field have basically taken the bold step of using the detectors, and some of the most prominent pieces of work using these detectors over the last few years are shown on this slide. The principle is simple. Instead of getting an integrated frame where you have a bunch of signal, including noise, as you see on this slide on the upper right-hand side, this is done by the work of Tamir Gonen and his lab. You can see that you can identify individual points of signal. And if you're lucky, you can map those to diffraction spots. They've been able to leverage this to determine structures to very high resolution. And the idea for coincidence loss is simple. We're trying to overcome the issue that these detectors count with a finite rate and that they aren't necessarily able to discriminate individual events in a single pixel if those events coincide with other events in neighboring pixels or in the same pixel at the same time. So thinking about a race car analogy, it's easy to tell whether or not a race car is crossing the finish line if it is the only one crossing the finish line at that time that you are looking at that finish line, and if you can discriminate it cleanly. But of course, if several cars cross the finish line at the same time in the same lane, it makes it a little bit difficult to know how many precisely counted that you could count. And of course, if a whole swath of them come together and are very closely matched, it becomes rather difficult to be able to count them all individually. And so you tend to undercount. And so we have been lucky to be able to test a lot of this on an Apollo direct electron detector manufactured by DE. It reads at a raw frame rate of about 2,400 frames per second. And we've been able to essentially simulate what the anticipated coincidence loss might be when you have an independent pixel or a correlated set of about 9 pixels. And what you can appreciate from these graphs is that the number of counted electrons is never matching the number of measured electrons, which are on the x-axis on the left-hand side of these graphs. Of course, the number of measured electrons plateaus, essentially dependent on the fundamental counting rate or the number of frames per second that you're able to count. events at. And if you go to very, very high frame rates or very, very high counting rates, then you're able to approximate the perfect counting rates. But in most of these cases, you're really only doing well at counting when you have very, very few electrons incident on any given pixel in your detector. Otherwise, you end up undercounting or miscounting. And what we found, at least for this detector, is that with a fluence, or with a total number of electrons per pixel per second, that's less than about 80, you could get reasonable counting with no more than about 10% loss, or 10 to 20% loss in counting. That's a challenge for diffraction, more so than for other methods, perhaps, because while for single particle and tomography and for the other methods, the signal is spread out evenly across the detector, here you have signal concentrated at very, very strong reflections, right? All of the signal is coming into those reflections at the same time. And so there isn't necessarily this direct relationship between the incident fluence on a sample and the amount of signal that might end up on any given pixel. Here I'm giving you an example of crystals of a particular small molecule acetylene ligand illuminated with a very, very low dose of electrons, 0.01 electrons per angstrom squared per second. And there are patterns on the right-hand side showing what you would observe with a conventional scintillation-based detector, CETA, and then with the Apollo. Of course, the noise level on the Apollo is very low, and you can see that there are very strong, sharp reflections, some of them exceeding counts of 20 or 30 electrons per pixel during this 1 second exposure. And so what that told us is that that is something to be wary of, and potentially undercounting might be an issue. And so we went about surveying different crystals and different parameters, different fluence parameters, to try to optimize what we might find is the best condition for diffracting from these kinds of molecules and these kinds of crystals. And so we chose to sample everywhere between 0.1 electrons per angstrom squared to 0.01 electrons per angstrom squared in incident flux, and then mapped as a function of given tilt series how many electrons were observed per given pixel. We mapped those distributions, and we also charted what the maximum counts were for any given frame. And you can see that those maximum counts sometimes exceed the 100 electrons or 200 electrons per pixel mark, indicating that when bright reflections come into the field of view or come into reflection condition, then you can end up with some momentarious or instantaneous momentary reflections appearing on the detector that are very bright and might exceed your thresholds for counting. Of course, what you can do as an alternative is basically crank down the dose and spread that dose over a broader region of reciprocal space. And so you can basically slowly rotate your crystals, slow down the experiment a bit, bring your dose down, and still accurately count from some of these molecules. Even if they diffract very well, you can maintain the counts to values that are lower than those anticipated for essentially undercounting quite a bit. And the benefit of doing this is that even though you've used a very low dose, you can get fairly accurate structures. Here I show you a sample of structures of acetylene ligand, of biotin, and of this thiostrepton peptide. And these are collected on the order of about a minute. And that data, of course, is for a single crystal, but you can merge a few if needed and determine these structures within about a few minutes. None of this at the moment is fully automated, but there is the potential with using these detectors to also use companion software that drives them and the microscope automatically. And so the promise is there to basically make this whole thing fully automated. In this third section, I'll talk more about the use of some degree of automation and the ability to scale down the experiment even further to map subregions of crystals that may have some pathology in them. And so a lot of this has been work that's in collaboration with Molecular Foundry. And there we're able to use the microscopes, in particular the team microscopes, to shrink the electron beam and basically make a parallel beam that is very narrow and has a very small footprint on the order of about 5 nanometers, full width half max. and illuminate subregions of a given crystal and then raster scan that beam. This is, of course, the type of spatial mapping that is employed all the time in 4D STEM. And so normally you would get HADF image, which is the spatial mapping of signal within the field of view. At the same time, you're also getting diffraction patterns for each of the illuminated subregions in that field of view. And we're making use of those diffraction patterns. And just to show you a comparison of the type of selected area electron diffraction that we might get from some of these crystals, from a subregion of that crystal subtended by the blue circle on the right-hand side, that compares to the type of diffraction pattern we would get now from this small red dot, which is the illuminated area. This is a single 4D STEM pattern where you can see a very clear lattice, still indicative of a well-ordered diffraction from that one small 5 nanometer area of that crystal. So we can raster scan that as we will, and that gives us the ability to ex post facto identify subregions of the crystal that we're particularly interested in and integrate the diffraction just from those regions in 3 dimensions. We're, of course, collecting a 4D STEM scan at various angles as we tilt the sample from typically something like plus or minus 40 or 50 degrees. And when we do that, we're able to map in 3 dimensions where we want our crystal, where we want our signal to come from, so we can identify the bounds of the crystal or a subregion of the crystal. Here are some synthetic diffraction patterns that have been coalesced from the individual diffraction data that is summed together or averaged together. And so after doing all of that, we're able to take all the diffraction data and determine an atomic structure from it. So this is the atomic structure of a peptide from a crystal that was illuminated by 4D STEM here. And ultimately, what we're moving towards is the use of even faster and better detectors to count more accurately and to be able to determine structures from as few assembled molecules as possible. This is an example also from NSEM, where we're able to illuminate crystals of this nickel DPPF small molecule. These are the crystals on the right-hand side. And of course, you can subtend any region you want of this and integrate the signal from that. You can see the integrated signal on the right-hand side. You can see it varies quite a bit because these are bent or warped crystals. And so we can select some subregion of that crystal and then determine the atomic structure from that. And that's where we're moving. That's the direction that we're moving in at the moment. We aren't fully there yet, but the promise and future of electron diffraction, I think, is moving in this direction of adaptive serial data collection, where we can potentially map diffraction and imaging at the same time and identify what structures we want to coalesce data from or profile the data in some sort of automated way. And I haven't really talked much about this, but there's a huge opportunity now in using machine learning and structure prediction for these approaches, especially for the structure solution portion of the process. And there's a lot to be done with respect to automation when it comes to the surveying portion and the mechanics of actually collecting the diffraction patterns. Now, hopefully, with all of that, we can shrink this currently somewhat laborious and lengthy process down to a matter of minutes or even shorter, and we can make it, hopefully, fully automated. And with that, I'll say that the majority of this work was done by my lab here at UCLA. In particular, this is the work of Nico Vlakis, Cameron Flowers, Amarneel Shah, and of course, going back to Dr. Marcus Gallagher-Jones, who's now at RFI, in collaboration with fantastic team members from our EPI project. This is Professor Yi Tung, Ben Tu, Jade Wang, and of course, our close collaborator and colleague, Professor Jose Nelson, who's now at Caltech, the entire team at NSEM, and also Colin Ofis, who's also on the call now, helping us clearly map out these bent lattices and trying to understand the diffraction patterns that we see from them. And of course, our collaborators at SLAC and all of you for listening. I'm happy to take any questions.
Jose, thank you very much for these very impressive results from diffractions to detectors and the biology. It's very impressive indeed. So I think for those questions, could you go into the Q&A portion of it? The first question is that some biological molecule require water molecule for activity in active sites, but I see that for microelectron diffraction, the sample are dry or powders. How do you deal with these limitations?
That's an excellent question. I may have breezed through this, but there are really two main ways to get samples on the grid for these experiments. And one is if you have a dry powder and your molecules are fine and ordered and crystalline as a dry powder, then you can directly sprinkle that dry powder on the grid. If you need hydration, so if you have a crystal slurry, then we use methods that are essentially identical to the methods used for freezing single particles on a grid. So you'll put that slurry on the grid, you'll try to wick away as much of the excess mother liquor as possible. And then what remains are crystals that are hydrated by a thin film of mother liquor. And then you put those frozen crystals in the microscope and you diffract from them.
Okay. How many regular soluble protein crystal have you tried, which has been frozen by freeze punch?
Yeah, there are quite a few. I don't have a big survey in front of me now, but I should say that probably one of the best examples of this has been the work of the group of Xiaodong and the group of Tumir Gonan, who have collectively surveyed, I don't know, quite a few different types of crystals as an effort to try to demonstrate that you can either fragment the crystals directly or take fragments and slurries to try to interrogate their structures. In terms of novel molecules, I think, or novel structures, I think that's where the field is just starting to open up. And so many of the samples that we have investigated, we and others in the field have investigated, have either known structures or close relatives that are known. And so the opportunity is there for investigating truly unknown structures. I think that is just picking up now. And the other opportunity is to look at complexes. So one of the things that we started doing, as you saw, is looking at co-complexes of known molecular structures with either drugs bound or natural products or binding partners.
Mm-hmm. Okay, Bob has some questions.
Thanks. Well, thanks, Jose. Fantastic talk. Really very impressive. I'll ask a question which I ask our students and people who do the 4D STEM work. Do you have any correlation exact of an image taken directly from the specimen compared to a reconstructed image from the 4D STEM data?
Yeah, that's a great question. We don't have that, but it's something that we're very interested in, and it's something that we are working towards at the moment, or want to work towards at the moment, because in cases where you don't have an easy ab initio solution to overcome the phase problem, we think that that might be helpful. Also, we think that might be helpful when you're trying to disambiguate absolute stereochemistry of a sample.
Yeah, I'm wondering if Colin has any comment about that.
That's probably a longer discussion.
Okay, there's another question from the audience. Is there an upper limit in molecular weight for electron diffractions?
That's a great question. I should say that that depends on several factors. Fundamentally, I think it depends on the number of well-ordered repeat units you can illuminate and collect signal from. Of course, as things get bigger, the number of illuminated repeat units typically shrinks. And so what we're trying to figure out with some of these 4D STEM experiments is basically, how many repeat units do you really need that are well ordered to be able to get enough signal to get an atomic structure from that assembly. And by rough back of the envelope calculations, it looks like we can get pretty good signal from well below, from assemblies that are in size well below 10,000 molecules. And so the question is, how many molecules do you truly need? Can you get to 1,000 molecules? Can you get to 100 molecules? we don't know what that limit is yet. But of course, as molecules get bigger, it becomes a little harder to get well-ordered arrays of those molecules all illuminated by the electron beam. I'll tell you what can be done, all right, because I've sort of skirted the question so far. What can be done is that you can take a larger assembly, and if it's too thick, you can ablate regions of it that you don't want. Okay, you can either fracture it or you can mill regions you don't want away, leaving just a thin slab, a thin but wide slab of that material. Then, even if your molecules are relatively big, you have enough of them that you can illuminate simultaneously to get enough signal out. And I think that's been done, obviously, for many years with 2D electron crystallography, but it's being done again now with the use of film milling to ablate regions of the crystal that you don't want and leave a thin slab that contains the features you do want, and enough of them repeated that you get high resolution.
Okay, Dr. Han has some questions.
Oh yeah. Hey Jose,
Yeah.
very nice talk. I'm not working in the field, so my question may be naive. I'm just wondering, is it possible to combine imaging, for example, high resolution TM, with the 3D electron diffraction? Because from the TM image, you can extract some the structure factor phase information, and this information may be useful for structure determination. I mean, based on the diffraction data. I'm not sure if this strategy has been used or it doesn't make sense.
It's a fantastic question. It makes a lot of sense, and I think it's one of the best arguments for tychography. When you're natively recording diffraction information that is used to reconstitute an image, that image, of course, now has phase information, and you can use that to try to decipher features in the structure without having to otherwise solve the phase problem. So in other words, you're solving the phase problem directly from the diffraction data. I think alternatively, if you can't withstand the tychography process, then you can do some kind of hybrid experiment, as you mentioned, where you diffract from a subregion of a crystal or some portion of it, and then separately collect images in real space to try to combine the information. But I think the best marriage there is tychography as an emerging method.
Thanks.
There's a question from Michael Elbaum from Israel. And he asked a question, can you comment on the trade-off between different types of camera like Apollo, Falcon, K3, etc., or the hybrid detector like Dietrich's at the end? Do you have any working experience in comparison?
Yeah, we've used a few. Like I said, I think the initial challenge was just getting over this innate fear that we're going to burn the detector or that we weren't going to be able to measure accurate signal. Now I think we've used a K2, a K3, an Apollo, Vector's detectors. And fundamentally, I think what it all comes down to is being able to count as quickly and accurately as possible. So the faster you go in terms of frame rate, the better you are for diffraction, as long as you can still accurately detect, the weak signals that you need to detect. And as long as you have some way of dealing with all of those frames. So the nice thing about the Apollo, I should say, it's convenient for us because it has basically on-chip counting. It has a series of FPGAs that are built into the camera that essentially do the counting for you, and it's a frame-based counting. So each of the individual events is detected as a cluster of pixels, and then it's automatically assigned, a count and localized on a synthetic frame that you are then given by the detector. And so that's convenient. In other cases, we basically would have to do that ourselves, either by thresholding or centroiding or something else. And we've done that in the past. All of the cameras that we've used so far are still fundamentally limited by this counting rate. And that's why we have to worry about things like how much fluence are we delivering onto our crystals, how much are they diffracting, are they diffracting really strongly, how are the diffraction spots distributed across the detector, and so on. The only detector that we've got to use that doesn't really for which that doesn't really matter is these new generation of direct electron detectors, like the one that I mentioned from the Molecular Foundry in Berkeley, where essentially you're going so fast at 100,000 frames a second that it doesn't undercount very much. But then, of course, you have to deal with the fact that you have 100,000 frames every second and you have to figure out what to do with all that data. There you have a supercomputer, and so it's convenient.
So I have one question about some missing information due to the limit angle till in do you think that's not a limiting factors in some of these cases?
It's absolutely limiting. I think the problem is not new. It's been probably an even bigger issue in tomography for a long time, as you know. The benefit, I think, of crystallography is that if you're able to sample multiple distinct crystals that you can merge data from, the combined data then overcomes some of that missing wedge, some of those missing wedge issues. And I think that fundamentally leads us to want to sample many, many crystals from, or as many crystals as possible, and then sort of ex post facto figure out which to merge. Crystals at the nanoscale aren't perfect, and they aren't all identical. And so what you end up is with some unknown degree of polymorphism. And so sometimes the data merges better than other times, and you have to figure out how to discriminate what to merge. I think that's a problem that still has to be solved.
Okay, good. All right. Thank you very much for this outstanding presentation, Jose. This is
Thank you again for the invitation.
opening our eyes. Yes. Okay, Bob, let me return back to you.
Okay, yeah, thank you very much, Jose. That was terrific, and really bridges some of the things which Yuhan is going to be talking about next, and also what so many people in sensitive material science are also thinking about. So that's terrific. So our next speaker then will be Professor Yuhan, now at South China University of Technology. Yu has been doing some fantastic work over the years at King Abdullah University of Science and Technology in Saudi Arabia, and some really very, very impressive imaging of MOFs, metal organic framework, very beam sensitive materials over the years. So we're looking forward to a new career for you in China. Hopefully expanding even more from what he has done so admirably in Saudi Arabia. And I think you will be our first speaker, at least in the physical sciences, from China. The time difference is pretty brutal, so we really appreciate it. We've had speakers from Japan and so on, but it's very good that you joined us today, and you please tell us what you've been doing. Thank you.
Thanks, Bob, for the introduction, and good morning, everyone. I'm very delighted and truly honored to speak at this symposium, and I'm grateful to the organizers for inviting me. So yeah, today my presentation is titled "Low Dose Electron Microscopy Imaging of Highly Sensitive Crystalline Materials." Oops. Well, diffraction is a very powerful tool for determining the bulk structure of crystalline materials, as Jose just very nicely demonstrated. Well, we still need imaging to observe local structures, such as the surface of crystals, or the interface between crystals, or defects within crystals, because these local structures are not periodic, so they are not visible in diffraction. Well, with imaging capability, high-resolution imaging capability, for example, transmission electron microscopy, TEM, then we can directly visualize this local structure in real space. In the TM community, there is a very popular saying, make every electron count, which actually highlights the importance of low-dose techniques, because the electron beam can bring a lot of side effects into the specimen during imaging, including structure damage, phase transition, heating, charging, etc. So to minimize these side effects, we should always use the lowest electron dose possible. Right? So in fact, many materials are conventionally considered unsuitable for TM study because of their high sensitivity to electron beam irradiation. So once exposed to the electron beam, their structure will be immediately damaged. So a typical example is a metal organic frameworks, MOFs. So here, as you can see, under a very typical TM condition, the structures of MOF crystals are completely damaged, so leaving no structure information recorded in the image. Over the past years, my group has focused on low-dose, high-resolution imaging of sensitive materials under both TM and STEM modes. And more recently, we started working on 4D STEM-based tachography. And we are also interested in developing specimen preparation protocols for sensitive materials. Well, in today's presentation, I will focus on the imaging part. So in the TM mode, we first demonstrate that using direct detection electron counting camera can significantly reduce the electron dose required to produce a sufficient signal to noise in the image, so making the low dose imaging from impossible to possible. But this is not enough. On top of this, we still need to address some additional challenges that are associated with low dose conditions. So first, because we are dealing with the crystalline materials, so we cannot image them from random orientations. We have to find the zone axis prior to imaging. So that means we have to, because we have very limited quota of electron dose, so we must find the zone axis very quickly. Otherwise, the structure will be damaged during the zone axis searching process, and we will not have any chance to take image at all. So to solve this problem, we developed a method that enables one-step automatic zone axis alignment. So this method can effectively minimize the electron dose consumption for zone axis alignment, typically less than 1 electrons per square astron. Well, the second challenge is that how to precisely align the very noisy frames in the image stack. If we cannot do that, we cannot retrieve the high resolution information. But because of the dose, at ultra low dose conditions, the frame are highly noisy, so they cannot be precisely aligned using conventional methods based on feature matching or phase correlation. So to solve this problem, we developed a method that we call amplitude filter. So using this amplitude filter, we can achieve single frame-based alignment of the image stack, so we can get better resolution. And the last problem is how to determine the defocus value of the image. Because for TM image to be interpretable, we need to know the defocus, right? In HRTM, I mean, the common practice is to take a focus series. But now we are dealing with a highly sensitive materials. So even by using the new camera, we can obtain at most only one image before the structure got damaged. So with only one image, how to determine its absolute defocus value? We propose a new strategy to achieve this. Okay, so today I will skip these technical details of these methods, and if you are interested, you can refer to our publication. So combining these methods with the new camera, we have established the so-called ultra-low dose HRTM technique. So which allow us to acquire images with an electron dose as low as several electrons per square astron. And this ensures the structure integrity of highly beam sensitive materials like MOFs. So using this technique, we got this image from the same MOF materials discussed earlier, whose structure was completely damaged by conventional HRTM, as you may recall. Okay. So this comparison, I think, very well demonstrates the power of the ultra-low dose HRTM. And this technique works pretty well. It has allowed us to acquire high-resolution image for many morph materials for the first time, which were conventionally considered not imageable using TM. So our study focused on local structures of these morph crystals, such as surface, interface, gas molecules, defects, and so on. And because these local structures are very challenging to investigate using other characterization tools. And this technique is not limited to imaging morph materials. It can be generally applied to other beam-sensitive materials. For example, covalent organic frameworks, COFs, supermolecular crystals, porous gas, and so on. So like morphs, these materials were traditionally considered not imageable using TEM. So here I would like to share just one example that demonstrates HRTM can identify subtle structure features that might otherwise be overlooked. This is an extensively studied COF materials synthesized from these two monomers, TAPB and the DMTA. And because of these 3+2 connection configurations, and also because of there is only one type of a chemical linkage between the two monomers. So traditionally, people believe this COF has a very simple, very straightforward 2D hexagonal layered structure. So in each layer consists of 6 membrane pores with in regular hexagonal shapes, and all the layers are identical and they are aligned perfectly without any misorientation, so forming the so-called AA stacking mode. So if you look into the literature, there are more than 200 published papers on this particular COF material, and in all these papers, this structure was taken for granted without any question. So now we have the low-dose imaging capability, so we can take a look at the structure using TEM. So it's interestingly, we found that these materials actually contain 2 types of 6 membrane pores, but none of them has the regular hexagonal shape. So specifically, one type consists of 6 convex edges, okay, giving it overall a nearly round appearance. Okay. Well, the other combines 3 straight edges with 3 concave edges, so resulting in a shrunk pores with smaller pore size. And this is radically different from what people previously believed. So to distinguish these 2 structures, we refer to the structure that people previously believed as a monopore structure, and what we actually observed in the TM image as a dual-pore structure. Okay. A plausible explanation for the formation of a dual-pore structure is that the cis and the trans conformation of the diimine linkage coexist in the structure, which correspond to the curved and the straight edges respectively. Or in contrast, in the conventional structure model, people believe that this material contain only the trans conformation of the diimine bonds. Okay. So if our dual pore model is correct, there should be diffraction peaks at low angle regions, right? Because of its larger unit cell. Well, previously people didn't know the actual structure, and so they didn't pay enough attention to the low angle region. And so in the XRD study, they missed the low angle reflections. So now seeing that the unit cell is actually large, so we have conducted a small angle X-ray scattering measurement, because the SAX is more sensitive to the low angle signals. And indeed, in the SAX pattern, we observe a significant peak in the low angle region, along with several new reflections that have been missed in previous studies. So this result in turn confirmed that our dual pore model is correct. And taking one step further, we use a 3-dimensional electron diffraction to determine the unit cell. The results shows that the unit cell is larger than previously determined not only in the AB plane, but also along the C direction, suggesting that actually the adjacent layers are not identical, but they are alternating. So based on these understandings, we are able to construct a more accurate structure model for this well-known and well-studied curve. In this new model, each layer consists of 2 types of 6 membrane pores, with adjacent layers flipped relative to each other. And this dual-pore AA prime stacking mode, this model match the HRTM image perfectly. Okay. So to summarize, I mean, in this study, by using the low-dose, ultra-low-dose HRTM, we discovered that a seemingly simple and long-accepted curve structure is, in fact, inaccurate. Well, in addition to the bulk structure, we also see abundant green boundaries and defects in this curve. For example, there are, as you can see here, 5 membrane pores and 7 membrane pores along the boundary between 2 greens with a 30-degree misorientation. And there are double 5 membrane pores and 8 membrane pores along the coherent green boundaries. So these observations remind us of graphene, which has a similar green boundary structures, albeit on an atomic scale. Here we are at nanometer scale. Well, although the ultra-low dose HRTM has proven successful in many applications, it typically requires image processing to render the image interpretable. And this image processing not only demands expertise, but is also prone to generating artifacts. So as an alternative, we are also exploring the commercial IDPC STEM technique for low-dose imaging. Well, compared to the conventional STEM modes, IDPC has some advantages. For example, it has a higher electron dose efficiency, and it has the ability to image light elements and heavy elements simultaneously. Well, compared to HRTM, the IDPC image can be more easily interpreted. The high electron dose efficiency make IDPC STEM a good choice for low-dose imaging, while the ability to image light elements and heavy elements simultaneously make it suitable for studying host-gas interaction in nanoporous materials. And this is probably why IDPC STEM has been extensively used to study zeolites. Zeolites are inorganic porous materials. For example, we investigate the distribution of metal clusters in zeolite ZSM5. And similarly, a group in Tsinghua University in China use IDPC STEM to visualize the adsorption of the hydrocarbon molecules in zeolites. And we have also used IDPC STEM to identify a lot of structure defects in another zeolite called EMM17, including stacking faults, as you can see here, and some diverse structure defects that cannot be easily determined from the 2D image, but we can see there are many structure defects in different types. And we have also used IDPC STEM to study organic nanoporous materials, specifically polytriazine imide, PTI. Right? So PTI has gas molecules, lithium chloride in the channels, and these gas components can be removed partially or completely by acid treatment. So through imaging, we provide direct evidence for the removal of these gas molecules from the channels of PTI. As you can see here, some channels are already empty, while the others remain occupied. Right? So this is a very good demonstration of the IDPC STEM for host-gas interaction study. Well, zeolites and PTI are considered as beam sensitive, but they are not extremely sensitive. So we wonder whether IDPC stem can be used to image extremely sensitive materials like MOFs. And then we gave it a try, and we found that under optimal conditions, it's possible to acquire IDPC stem image for some MOFs. The obtained resolution here is already comparable to HRTM. Well, the advantage here is that the images are nearly directly interpretable. Well, however, I think I need to emphasize that the success rate of IDPC for MOFs is rather low. This is because IDPC stem require precisely focused beam to achieve a high resolution. Okay. So the structure is, when the materials are sensitive, then the structure is very likely damaged during the focusing process. So with the development of ultra-fast pixelated electron detectors, 4D STEM is becoming more and more popular. Tachography is one of the most active research areas of 4D STEM. So compared to conventional STEM, it has some advantages, including not requiring precise focusing to achieve high resolution. So for sensitive materials, the ability to image without requiring precise focus is, of course, is a significant advantage. So we began our experiments with zeolite samples because they are sensitive, but they are not extremely sensitive. Right? Here are the conditions for our 4D STEM data collection. I won't go into details, but just want to highlight that in this particular experiment, the total electron dose we used was approximately 3,500 electrons per square astron. And this is our reconstruction results, and we benchmark it against IDPC STEM that is considered the state-of-the-art for zeolite imaging. So we can see that tachography outperform IDPC STEM in both resolution and image contrast, even though the specimen is about 4 times thicker. Right? So the silicon and oxygen atoms in the zeolite framework are all clearly resolved in the tachography reconstructed image. And the tachography reconstruction also offers a resolution in the third dimension. Although the resolution in this direction is not, it's only at several nanometer level rather than atomic level, it's good enough to identify the integrals between 2 different zeolite phases along this direction. Well, in the TM community, many groups have made significant efforts to pushing the resolution limit of tachography, right? So resolution better than 20 picometer has been achieved by different groups, which is indeed very impressive. Well, our focus is a little bit different. We are trying to push the limits on electron dose. So we were wondering whether tachography can be performed at a dose level, let's say as low as 100 electrons per square astron, to make it useful for highly beam sensitive materials. So we first used simulated 4D STEM data, and we found that at such a low dose condition, even with the simulated data, the reconstruction is very challenging. So achieving a reasonable reconstruction is only possible when an appropriate conversion angle is used. If the conversion angle is too large, then the iteration fails to converge. So the reconstruction is so challenging because at such a low dose level, the CBAD pattern have extremely sparse and weak signals. On average, each CBAD pattern contain only about 100 electrons, and all the signals are single electron events. So therefore, optimizing the data collection conditions is crucially important for the reconstruction under such a low dose condition. And the more simulation data confirm that using a relatively small convergence angle, specifically in this case is a 10 millirad, is essential for achieving successful reconstruction under ultra low dose conditions. I think there are several reasons for a smaller alpha being more favorable. First, for limited dose, a smaller alpha gave us stronger signals in the seabed pattern. And well, at the same time, a smaller alpha also means a lower degree of a probe aberration. And it also prevents the generation of overly large probe size under defocus conditions. So these factors are all favorable for reconstruction. Well, using the optimal conditions identified through simulation, we conducted 4D STEM experiments on two morphs, zirconium BTB and NU1000. And the results are quite encouraging. As you can see here, we have successfully reconstructed the tachography image for zirconium BTB and with a resolution close to 2 angstrom using a 60 nanometer defocused probe. Yeah, and because the probe was unfocused, so the conventional STEM image collected using the same probe of poor resolution, right? And this demonstrates the advantage of electron tachography discussed earlier. And the reconstruction for the other morph NU1000 ends up with an even higher resolution. With this resolution, we can resolve the neighboring zirconium atoms within the metal clusters. And with this resolution, we can also identify some interesting structure features in this material. For example, in this area, we see that there are a lot of actual clusters in the channels that are supposed to be empty channels, but in this area, we see actual clusters. And on the surface of the crystal, we can see we can identify the surface termination modes. We found that this crystal surface is exclusively terminated by the triangular channels rather than the hexagonal channels. All right, so finally, let me share some reflections on the respective advantages and the limitations of the low dose technique I discussed today. HRTM, I personally believe HRTM remains the most efficient technique for extremely sensitive specimen because it can easily produce high magnification image with an electron dose as low as a few electrons per square angstrom. However, interpreting a low dose HRTM image can be quite challenging. Well, ITPC STEM offers straightforward image interpretation, but the problem is that it requires precise focusing. So overall, the success rate for image acquisition is low. Well, on the other hand, 4D STEM tachography doesn't demand stringent data collection conditions. But currently, the reconstruction success rate with low dose data is low. And this is the limitation of 4D STEM tachography based on our experience. All right, I think I will stop here by thanking people and organizations that support our research. And in September 2023, I moved from Saudi Arabia to China, and I joined the South China University of Technology, where we have a new center for electron microscopy. And this is our center's logo. And this logo is a cartoon representation of an electron microscope and designed to resemble the Chinese character for electro, dian, right? And these two sides represents the two coils, the very important components in electron microscope. And this coils looks like the English letter E, right? Well, looking from the side, they appear as the letter M. So E and M together stand for electron microscopy. So yeah, whether in Chinese, in English, or its overall image, our logo embodies the concept of electron microscopy. All right. Yeah, I stop here, and I will take any questions you may have. Thank you.
Super. Thank you very, very much. You had that was really terrific. Good overview of some of the advanced techniques as well. I had a quick question about the tychography reconstruction that you're using. Is this your own reconstruction, or are you using David Mueller's or Collins, or how are you doing the reconstruction of the tychography data?
Yeah, we didn't develop our own codes for tychography. I have backup slides. Yeah, basically, we slightly modify the code developed by David Muller's group. Yeah, these are the reference that we used. Yes.
Colin, please.
Beautiful work, you. That's amazing.
Yeah,
results.
thank you, Colin.
One question about, so we've also had very similar results with the ultra low dose tychography struggling to converge it. And we've had better luck doing things like single sideband, WDD, et cetera. But my question for you is, have you tried taking your DPC signals and doing a tychographic reconstruction of them?
Taking what DPC?
So if you have your 4 DPC channels and then essentially doing a 4-pixel tychographic reconstruction, so iteratively solving and deconvolving the probe.
No, we haven't tried that.
I'll send you an email about that then.
Sure. So what's the potential benefit of doing that?
Speed, right? And being able to collect a lot more probes, right? And somewhat being able to deconvolve, defocus, so you don't have to waste dose getting the perfect illumination conditions.
I see. Okay, thank you so much, Colin. Yeah,
beautiful work.
Please send me the reference or your primary results, please.
Kate.
Yeah, thank you very much. That was a really excellent talk and some great work. I had a short question, but I was curious, at some stage you said you got the spacing along the C-axis for these materials that were kind of layered in some way. And I'm curious how you got that when you were looking down. Was that a tilting?
Oh, I'm sorry, maybe I didn't explain clearly enough. That results was not from imaging, it's from 3D electron diffraction data. So, okay, I can show you. Yeah. So we have collected 3-dimensional electron diffraction for this curve. So we can determine the unit cell 3-dimensionally. Yeah.
Got it. Okay, thank you.
If there are any more questions from the audience.
Jose has Jose raised his hand.
Oh, sorry.
Yeah, beautiful work, you. Really fantastic. I think one of the most striking was the high resolution tychographic images that you got at low dose. I wonder if you illuminated the same area with a parallel beam, what the resolution of your diffraction pattern would look like. Have you tried that? So how does it compare, basically, what you're getting from tychography to the resolution and diffraction patterns from just a parallel beam experiment?
Okay. We didn't do a systematic comparison, but if I think it's comparable because for MOF materials, I think even in the electron diffraction pattern, the highest spatial frequency, I think it's around 1 astron or something like that. Yeah, it's difficult to get sub-astron resolution even with diffraction. But I will double check that and I will let you know.
Because this goes back to your previous suggestion. I think this might be a really interesting material to try that on, to basically collect a very, very low dose electron diffraction data set, in the conventional sort of continuous rotation micro-ED style, and then with the typographic reconstruction that you get, try to see if you can seed phases.
Sure, yeah.
Yeah.
Jose, just for your information, in our center, actually, we have a colleague specialized in micro-ED and who graduated from Stockholm University, from Xiaodong's group. So yeah, he has collected a lot of 3D and micro-ED data from MOF materials, MOF and COF materials. Yeah, I will double check with him and see, yeah, what's the resolution limit for in diffraction pattern.
Yeah, with little overhead in terms of added electrons per angstrom squared.
I'm curious, about your effects of defects. With the imaging, of course, you can see defects like grain boundaries or stacking faults and so on. But if you're not doing that direct imaging and you're relying on summations to form a better crystal structure model, what effect does the defects have on which you may or may not know is there on the summations when you try and improve the data for atomic structure of crystalline materials?
Bob, can you repeat your question? I don't think I get your point very well. So you mean assumption of what of the local defect structure?
Yeah. So what you've shown with the high resolution images that you can image the defects.
Yeah.
But sometimes when you want to have really good structure analysis of a beam sensitive material, you often sum from one unit cell to the next unit cell to get the structure better. And so I'm wondering then what effect the defect, if there's a crystalline defect there, has on that summation. I mean, how many unit cells then would you need to overcome it, as it were, or does it have any effect or no effect?
Okay. Yeah, but I think you're asking about the real space averaging of multiple unit cell to enhance the signal to noise. But we actually it's not. We are very cautious to do that for local non-periodic structure, because in principle you can only do the real space averaging for periodic structures, right? So yeah, we have done that once for surface termination structure. We assume that all the surface termination adopt the same termination modes, and then we do that. But for the grain boundaries, we don't think it's appropriate to do the real space averaging. Yeah.
Okay, so it also points to imaging being a useful component of the analysis, as well as just diffraction without the imaging.
Great.
Okay, are there any other questions?
Yeah.
Thank you, Professor Han, for your wonderful talk. Just curious, like, have you tried like cryogenic protection for your sample just to make it more dose tolerant?
You mean cryo?
Yeah.
Oh, okay. Yes, we actually we compare the dose tolerant for some MOFs and some perovskite materials at room temperature and cryo temperature. We found that cryo temperature in some cases indeed helpful for enhancing the dose tolerant, but not significantly. Typically, is for example for hybrid perovskite materials we studied at the room temperature is beam threshold is about 11 electrons per square astrom. At cryo temperature, the threshold has been improved to 36 or something like that, only 3 times, but still very, very sensitive. So yeah, we still need to use the low dose technique, yeah, to image. Yeah.
Yeah. So just curious, like how you freeze the sample, like doing this cryo experiment.
No, we didn't. Because in our sample, there are no liquids involved, so it's dry sample. So we simply use a cryo holder, just lower the temperature, and without freezing anything. Yeah.
Got it. And I think Michael also raised a hand. Yeah. Michael, you're allowed to talk now.
Okay. Hi, this is Mike Schmidt, and
Hi.
for all of the for Jose and for you and for Bob, when you take an image of a three-dimensional crystal, any individual one of the images, you can figure out the amplitude and the phase, of course, in the images have both of those in them. But then to correlate that in 3 dimensions with an orientation that's different from that one, you have to get the phase origin in 3 dimensions correlated among those images. And that was always the most difficult thing, is to correlate the phase images of images that are collected at different angles or different orientations from all those projections.
Yeah, it's a great point. It's not a trivial problem, I would say. And really at certain angles, it may be easier than others. If you're in a zone, for example.
Oh, yeah.
Yeah, I agree. This is not trivial. Yeah.
How accurately are you getting the zone axis, you?
How accurate I can get the zone axis? Okay, it's okay, I'm not sure how to define the accuracy in this case, but from the diffraction pattern, if you look at the symmetry of the diffraction pattern, or from the final image, I think we can get it quite precisely and accurately. So yeah, it's maybe minus plus 0.05 degree. That is limited by the stability of the geometry. So yeah. I think we have discussion in our publications, but I don't remember the exact value of the minus plus range. Yeah, but definitely less than 0.1 degree. Yeah.
Good. And so in terms of the images, what if you are you doing aberration correction for the so for the imaging, and in which case do you use what CS value are you using for the aberration correction?
Okay. Yeah, I think the CS correction only affected the resolution, but the whole process is the same. For example, the first example I share is was not this one. The image of ZIF8 I show here was acquired from an uncorrected Titan microscope.
I noticed that. So
yeah.
So does correction help you?
Oh, yes, of course. Correction will definitely improve the resolution. Yeah.
Do you go for negative CS imaging or
No. It's still yeah, positive CS.
So what CS value are you going for then when you're correcting?
Oh, that's we just try to minimize the CS as much as possible.
Okay.
Yeah, we didn't play with the CS value. Yeah.
Okay. All right. Are there any other questions from the audience and Q&A? I don't think so. Then Actually, I think that these have been so intense talks, really very, very impressive, both Jose and Yuhan. Thank you very much.
Thank you.
So, Hua, do you have
Thank you.
some final comments? Is Hua there?
You're muted.
Yeah.
Okay, I'd like to thank both Jose and you for these inspiring talks, and I learned a lot about these approaches. And it's very exciting to see how the two fields can eventually merge to cryogenic electron imaging and diffractions. And I think there's a lot of exciting area, particularly the detector developments and also interpreting the images. So I look forward to more discussions in the next few lecture series.
Thank you.
Thank you.
Colin, do you have anything to say?
Nope, great talks, and totally agree with Hua. I'm loving the intersection between diffraction and imaging.
Ah. And Kate?
Yes, thank you all. They were wonderful. And thank you for joining us at the unusual time zone. I hope you get a good
It's
sleep
okay.
after this.
It's my pleasure.
Thank
Yeah,
you
but
both.
it's the time for me to go to sleep. Yeah.
Very well deserved. I'd like to thank Yi-Che and Jane for setting up the rehearsals and this session. So Yi, thank you very much again. And our absent colleagues who are traveling, Jen and Professor Yi-Che. Thanks again to Jose and Yuhan for brilliant talks. And we will see everyone after the holidays. And January the 13th, the second Monday, or first working Monday, really, in the new year. So have good holidays and keep up the good work until the end of the year. And then we'll start 2025 afresh. Thank you very much, everyone. Bye-bye.
Thank you.
Hi.
Bye. Yeah.